Everyone, welcome back to my channel. I am A. Purnaseshan, student of Sri Venkateswara College of Engineering, Bangalore, USN 1VE22IS001, Department of Information Science and Engineering, Subject Theory of Computation, TOC. Today, the main topic of our presentation is problems that computers cannot solve, the Turing machine. The power and limitations of computers have been a topic of fascination for decades, with the Turing machine serving as a fundamental theoretical model. While computers can solve a wide range of problems, there are certain tasks that remain beyond their capabilities. In this presentation, we will explore the problems that computers cannot solve, the insights provided by the Turing machine, and the implication for the future of computing. Introduction to the Turing machine. Turing machine is a combination of tape, control unit, and read-write head. Tape. The Turing machine operates on an infinitely long tape, divided into cells, each of which can store a single symbol from a finite alphabet. Control unit. The control unit, which is the brain of the Turing machine, follows a set of rules to determine the next action based on the current state and the symbol read from the tape. Read-write head. The machine has a read-write head that can move left or right, reading and writing symbols on the tape as it goes. This is all about Turing machine. The halting problem, undecidability and implications. Let us discuss one by one. The halting problem. The halting problem asks whether a given Turing machine will eventually halt or run forever on a given input. Alan Turing proved that this problem is undecidable, meaning there is no algorithm that can solve it in all cases. Undecidability. The halting problem's undecidability demonstrates that there are problems that cannot be solved by any Turing machine, no matter how powerful the machine may be. This has profound implication for the limits of computation. Implication. The undecidability of the halting problem shows that there are inherent limitations to what can be computed, even with the most advanced computers. This has important philosophical and practical consequences for the nature of computation and the problems that can be solved by machines. Gödel's incompleteness theorem. Gödel's incompleteness theorem. Kurt Gödel, on groundbreaking work on the limitations of formal systems, has profound implications for the limits of computability. His incompleteness theorem states that any sufficiently expressive formal system will contain statements that are true but cannot be proven within the system. Implications for Turing machines. Gödel's incompleteness theorem suggests that there are truths that cannot be captured by any Turing machine, even the most powerful. This further reinforces the idea that there are inherent limitations to what can be computed even in the theory. The search for completeness. The quest for a complete and consistent formal system that can capture all mathematical truths has been a driving force in the field of computability theory. Gödel's work has shown that this goal is unattainable, leading to a deeper understanding of the limitations of formal systems and computation. Limits of Turing machines. Infinite tape. The Turing machine model assumes an infinitely long tape, which is an idealization that cannot be realized in physical computers. This highlights the need to consider practical limitations when applying the theoretical model. Finite memory. Despite the infinite tape, the Turing machine's control unit has a finite number of states, which limits the amount of information it can store and process. This has implications for the types of problems that can be solved by Turing machines. Deterministic nature. Turing machines are deterministic, meaning that for a given state and input, the next action is uniquely determined. This contrasts within the problem with the probabilistic nature of some real-world computation, such as quantum computing, which may require a different theoretical framework. Practical limitations. While the Turing machine model is a powerful theoretical construct, it does not account for the practical limitation of physical computers, such as energy consumption, heat dissipation, and the physical constraints of hardware. These factors can also impact the types of problems that can be solved efficiently. Recursive and recursively enumerable sets. Recursive sets. Recursive sets are those that can be generated by a Turing machine that always halts. These sets represent the problems that can be solved by a Turing machine in a finite amount of time. Recursively enumerable sets. Recursively enumerable sets are those that can be generated by a Turing machine, but not necessarily in a finite amount of time. These sets represent the problems that can be solved by a Turing machine, but may not always halt. Diagonalization is a technique used to prove the existence of sets that are not recursively enumerable, demonstrating the limits of what can be computed by Turing machines. The Turing degree hierarchy. The Turing degree hierarchy is a way of classifying sets based on their computational complexity, with recursive sets at the bottom and non-recursive sets at the top, highlighting the range of problems that Turing machines can and cannot solve. Diagonalization and the Turing machine include listing Turing machines. One way to explore the limitations of Turing machine is to try to enumerate all possible Turing machines and the sets they can generate. Diagonalization. However, using a diagonalization argument, it can be shown that there are sets that cannot be generated by any Turing machine, demonstrating the inherent limitations of the model. Implications. The diagonalization technique reveals that there are problems that cannot be solved by any Turing machine, no matter how powerful it may be, highlighting the fundamental limits of computability. The Turing degree hierarchy. Recursive sets. At the bottom of the hierarchy are the recursive sets, which can be generated by Turing machines that always halt. These represent the problems that can be solved in a finite amount of time. Recursively enumerable sets. Above the recursive sets are the recursively enumerable sets, which can be generated by Turing machines that may not always halt. These represent problems that can be solved but not necessarily in a finite amount of time. Non-recursive sets. At the top of hierarchy are the non-hierarchy sets, which cannot be generated by any Turing machine. These sets represent problems that are fundamentally beyond the capabilities of the Turing machines. Quantum computing and Turing machines. Quantum computation. Quantum computing, based on the principle of quantum mechanics, offers a fundamentally different approach to computation compared to the Turing machine model. Quantum computers can potentially solve certain problems much faster than classical computers. Limits of quantum computers. While quantum computers may be more powerful than classical computers for certain tasks, they are still subject to the limitation of computability theory. Quantum computers cannot solve problems that are fundamentally undecidable by Turing machines. Relationship to Turing machines. Researchers are still exploring the relationship between quantum computing and the Turing machine model. Understanding the capabilities and limitations of both classical and quantum computation is essential for advancing the field of computer science and solving new problems. Philosophical implications and future directions. The nature of computation. The insights gained from the study of Turing machines and computability theory have profound implications for our understanding of the nature of computation and the limits of what can be computed. Artificial intelligence and beyond. As we continue to push the boundaries of what computers can do, the lessons learned from the Turing machine model will be crucial in guiding the development of new computational paradigms such as artificial intelligence and quantum computing. Philosophical implications. The study of compatibility theory also raises deep philosophical questions about the nature of intelligence, the limits of knowledge, and the relationship between formal systems and the physical world. Future directions. As we continue to explore the limits of computation, new and exciting directions in computer science, mathematics, and philosophy will emerge, leading to a deeper understanding of the fundamentals nature of information and computation. This is all about Turing machines and its limitations and what computer may not solve when it comes to Turing machines. Thank you.